We'll move on to our next conservation drainage practice, the practice of blind inlets. We'll also touch on the topic of NRCS standards. We talked about surface inlets, surface intakes, tile risers in previous weeks. The point with a tile riser or a surface inlet is that these are critical parts of our drainage systems because they're essentially direct connections from the surface of the field, from ponded areas, straight down to the tile drainage or the subsurface drainage system. That allows the wettest parts of the fields to drain relatively more quickly than if you did not have that direct connection there. Surface inlets also present challenges for water quality though, mainly because this is one of the important ways and one of the main ways that sediment gets into our tile drainage system, which of course tile drainage water tends to be relatively clear unless you have a surface inlet present on your drainage system. In addition to sediment getting into the drainage system, we have sediment-bound phosphorus or particulate phosphorus that can get into our tile drainage system in this way. So enter the practice of a blind inlet. A blind inlet is a type of French drain where a perforated pipe is placed at the bottom of an excavated pit that's then backfilled with pervious media like sand or gravel. The best way to describe this practice is to just walk through the construction of a blind inlet. First, an excavation is made in the field around where the existing tile riser or surface inlet is, and you excavate down to the level of the drainage system. A geotextile fabric is usually laid in the bottom of the excavation, though that's not shown in this picture. And then you lay the collection pipes on top of that geofabric. Those collection pipes you see in the picture, you can just barely see some holes in those collection pipes. This is the collection system to collect that infiltrated surface ponded water that's infiltrated through the soil, collect that and route it into the subsurface drainage system. On top of that collection system, you fill with gravel media, typically with coarser media like the bigger stuff, the bigger gravel at the bottom, and then smaller media as you fill up towards the top. And then for a blind inlet, the top is covered with soil. Obviously, that's easy to remember because once the blind inlet is done, we are essentially blind to seeing any kind of inlet because it becomes invisible in the field. Geotextile generally is used to separate the top sand or gravel layer from the soil, which goes on the very top of the blind inlet, which this illustration illustrates all those concepts nicely of the different media that are required. And of course the plumbing is all connected along the way into the larger existing drainage system. The term gravel inlet and blind inlet, those terms are often used interchangeably, although they are technically different terms. There are technically different practices. The difference is that at the time of construction of a gravel inlet, the uppermost or the top layer of gravel or sand is left exposed. You don't cover it over with soil. That's opposed to blind inlet where you cover the top over with soil, so you don't really physically see anything in the field in terms of the inlet. However, with a gravel inlet, when you leave the gravel exposed at the surface over time, the sediment that's coming from your field, from the surrounding depressional area, that sediment will cover over the gravel. So over time, gravel inlets essentially turn into blind inlets, but they are just considered distinct practices because at the time of installation or construction, the practices are different. An additional nuance here with terminology is that the NRCS provides federal incentive payments for the practice of blind inlets and gravel inlets under the Conservation Practice Code 620, which is called underground outlets. The nuance here is that the Conservation Practice Standard 620 applies more broadly to other types of inlets other than just blind inlets and gravel inlets. And you can see the general purpose for Conservation Practice Standard 620 is a little bit more broad, is a little bit more general than just applying to blind inlets. The purpose of this Conservation Practice Standard is, again, more broadly to just convey ponded surface water safely rather than that water causing flooding or erosion. The idea of a blind inlet, in my mind, really fulfills the purpose or the intent of the idea of conservation drainage. Blind inlets do the same thing that a surface inlet or tile riser does, helping to drain quickly the lowest parts, the ponded parts of the field, But it also adds an additional benefit of trapping sediment, so that sediment's not getting into the drainage system. This is a good balance between meeting agronomic goals and meeting environmental goals, which is what the idea of conservation drainage is all about. There's also an additional benefit in terms of agronomy or infield management, because you don't have to farm around those tile risers anymore, so you don't have to worry about hitting those with your tractor. I also think there's an additional benefit not listed here. There's less sediment that gets into your tile system, so there's less potential for clogging or reduction in flow capacity due to accumulated sediment in the tile pipes themselves or the drain pipes themselves. Blind inlets are a pretty easy practice, low maintenance with a 10-year life, estimated 10-year life. The cost of the practice depends on the size of the blind inlet that you construct and also the availability of materials like the gravel and the sand. But generally, these blind inlets have been running between $1,500 and $3,000. The mode of action, or the mechanism for how this practice cleans water, should be pretty obvious. The gravel filters the sediment out from the water as the water flows through the media. It's just a filtration process, a physical filtration process. This means the sediment accumulates at the top of the blind inlet rather than flowing through the water and getting into the subsurface drainage system. I like this from a holistic standpoint because you're keeping the soil in the field. The soil might have moved a little bit from its original location in the field, but you're still keeping all of the soil in the field. There is an important nuance here in terms of water quality, in that the addition of a blind inlet to a field that did not already have a surface inlet or a surface intake or tile riser will actually decrease water quality. So just on its own, in any context whatsoever, a blind inlet is not necessarily a water quality benefit. A blind inlet provides a water quality benefit if you're using it to replace an existing tile riser or an existing surface inlet. In that case, there is a water quality benefit because you're reducing the amount of sediment. However, if you don't have an existing tile riser or a surface inlet, and you have a ponded area and you put a blind inlet in, you will actually increase the amount of sediment compared to not having any sort of inlet structure present already. So from a water quality perspective, the benefit of installing a blind inlet is only realized when the blind inlet replaces an existing, what we call open inlet. So how well does this practice of blind inlets work? These are values that I'm showing you from the Chesapeake Bay watershed for both a blind inlet and if you actually use a phosphorus-absorbing material mixed in with the gravel. So that's the second row, is a blind inlet using phosphorus-absorbing material in there. As you would expect, the sediment removal efficiencies are excellent. I would even consider these 60% values a little bit conservative. But unfortunately, there hasn't been a whole lot of research done on blind inlets, especially research with good valid controls, because it is a practice that you have to construct at the field scale in it, so it's hard to have a control unless you have many, many years of monitoring at paired sites. The study design gets complicated. Moving to total phosphorus reduction, most of the total phosphorus removed for the regular blind inlet case, the 40% TP reduction, is due to filtration of particulate phosphorus that's associated with the sediment. But if you do the more advanced option of using a phosphorus-absorbing material mixed in with your gravel or your media, you do get some additional removal of dissolved phosphorus due to that phosphorus-absorbing media that holds on to dissolved phosphorus. And that's why the TP value, the TP reduction efficiency is higher for the more advanced option, 50% versus 40%. See you next time.